Okay, this screencast is going to cover the idea of describing motion using diagrams. We call them motion diagrams, or if we add some more information and it helps, we often refer to them as motion maps. So really we have multiple ways to describe a motion. One way is to graph that motion. Might graph position versus time and look for the shape of the graph, which way it's headed, the slope, different data. We can use an equation, like if it is linear, it might be y equals mx plus b as a generic form. Or we can track the location in some kind of picture format. That's what we mean by the motion diagrams. Okay, so in this one we are going to look at a car that's moving, and we're going to determine if we think it's getting faster, slower, or changing direction, which means it's accelerating. And if it is accelerating, we're going to figure out which way it might be going. So when we first look at these, a picture of something like a car, it's a pretty large, complex picture. We want to simplify it, so often we will pick one part of the car, like say the front wheel, and we'll make our motion diagram of that. So what you really want to look at is what is the location of the blue dot compared to each other of the other blue dots. Now each of those dots is made of regular intervals, say 1 second intervals or half a second intervals. So if we look at the spacing between the dots, if the car is getting faster, it should cover more distance in that given time period. Higher speed means more distance per time. If the car is slowing down, it should cover less distance than it does in previous time intervals. If it is staying at a constant speed, we should see a relatively constant interval. In this case, the intervals are constant between the dots. They are of equal space. And we're moving along a single line, so we're not changing direction. So I would say no, we are not accelerating, and therefore I don't have to worry about the direction of the acceleration. There is none. Okay, and the next one. Now again, I want to pick out one wheel. In this case, I'm going to pick out the back wheel because I can't really see the front wheel on the first picture. Alright, now here's the first interval. Here's the second interval. There's an ever-increasing third interval, fourth interval, and fifth interval. Okay, so the intervals are not constant this time. We get more space per picture. That indicates our distance is going up per picture. If we're covering more distance, then that indicates our speed is increasing. Speed is the magnitude of velocity. So if the speed is increasing, the velocity is changing. Therefore, yes, by definition, acceleration is the rate at which velocity changes, the rate of change of velocity. Now in this case, we are getting faster as we move to the right. So that means that the direction of the acceleration must be in sync or the same as the velocity. So I'm going to say that the acceleration is to the right. The acceleration vector and the velocity vector, their directions need to match if the object is to get faster. Okay, let's look at the next one. I can pick the front wheel this time. And if you look at the picture, hopefully you can see that the gap between is pretty consistent. It's pretty much the same gap all the time. That again means we have equal space. That means we have equal distance. And that means we are going to have no acceleration because we're moving on a straight line. We're not changing direction. Okay, and this next one, I can pick the front tire. Now this time it's not quite as obvious. maybe perhaps as the first one, but there's that space, and there's that space. That is a little bit longer than that. And then from here to here, we're getting to a point where it's somewhat similar. And then from here to here, that's a little bit longer. So it looks like we've got an increase, although much slighter than we had in B, of our velocity. Our speed is getting higher. So we are going to say it's accelerating, and again, the velocity and acceleration vectors need to match in direction to get faster. Okay, and then E, here's our first picture, here's our second, here's our third, fourth, fifth, and oops, 6 is kind of covered up. Probably I should use the back wheel, but this will work. Hopefully it's obvious that we're starting with a pretty long interval here, and then our interval is getting shorter and shorter and shorter and shorter. So in here we had an increase of space, so we got faster. Here we have a decrease of the space between pictures, the interval. That means again our distance traveled is going down. Since speed is the rate at which we change our distance and our rate is constant, that means our speed is going down. Since speed is part of velocity and acceleration is the rate of change of velocity, then yes, we are accelerating. Now this time we're moving to the right, but we are slowing down. In order to slow down, our acceleration has to be opposite to our velocity. So in this case, our acceleration direction is actually to the left instead of to the right. Okay, in diagram D above, the cars are moving leftward and traveling backwards. What would be the direction of the acceleration? So now in this case, we would see in D, if I change colors, we started out far apart and we started getting closer together. Now that indicates that as we moved to the left, we would have been getting slower. That means the acceleration would still have to be to the right. So if we looked at this backwards, the acceleration would still be to the right. Okay. The action that's causing us to change our speed isn't any different, but instead of slowing down, instead of speeding up as we did originally, we would now do the opposite and we would slow down. So the impact of the acceleration is the opposite. It makes us slow down instead of speed up, but the acceleration itself does not change. Okay. So that's one way to look at motion using a motion diagram. We'll look at a little more detail in the next screencast.